Hello everyone, today we're going to present our fluid mechanics project. So first of all, we wanted to present a little bit of introduction before we start explain furthermore about this project. So the project that we will conduct is pressure in the pipe. Flow in pipes will experience losses and will affect pressure distribution as well as velocity and flow rate at multiple locations or axes. The knowledge principle can be used to analyze this condition as well as CFD simulation. There are some objectives that we want to achieve, which are to perform experimental insulation flow exercise in hose pipes, to analyze pressure variation in hose pipe over a specific pipe length with two different configurations, to discuss the findings and an appropriate approach.
Assalamualaikum warahmatullahi wabarakatuh. My name is Bmmh2313-Fluid Mechanics, and I will present about the experiment procedure for my group. So we have three experiments, which is the water jet, the straight line configuration, or we call it as open loop, and then we have the closed loop configuration. So the first experiment, which is water jet, I will read the experiment procedure. For this part, we set the length of the pipe to be 3 meter, then let the water flow from the pipe. Secondly, we measure the height of the water flow and record the data. Thirdly, after that, we record the time taken and volume of the water from the pipe. So for this, the first experiment, we got the total, we got the volume of 680 milliliter for 2.25 seconds, and the height is 0.93 meter. So we go to the next experiment, which is straight line configuration, or we call it as open loop. So I will read the experiment procedure. Firstly, for this part, we already set up the length of this pipe as 4 meter. The distance of each hole is 0.63 meter. The total of hole that we need to do is 5 holes. Then secondly, next we open the tap up to maximum and measure the flow rate and record the data of the time taken. So for this experiment, we got a height of water of 4.25 meter and a volume of 185 milliliter for 2.25 seconds. So we go to the next experiment, which is closed loop configuration. So for this part, I will read the experiment procedure as well. For this part, we use T connector to make the closed loop and make 10 holes, which the distance between each hole is 0.63 meter. The length of pipe we use is 7 meter. Secondly, the next step, we measured the flow rate from the pipe using measuring tape, and we also record the time taken by using method. Let the water flow in beaker and set timer until 5 seconds. So for this part, we got a height of 1.20 meter and a volume of 180 milliliter for 5.32 seconds. So that's all from me. Thank you very much.
Assalamualaikum and hello. My name is Muhammad Aiman bin Muhammad Azam. For this part, I will explain about the calculation. Before we go to the calculation, this is the data that we get. Firstly, we will explain about the water jet project. Okay, the diameter that we use is for the pipe is 0.016 meter. Area for the pipe is 0.020 meter square. Time taken for the water jet is 2.25 second. Height is 0.93 meter. Volume that we get is 680 meter cube. Density water that we use for this calculation is 1000 kilometer cube. Alright, this is the formula that we use. Okay, firstly we calculate the flow rate. the formula that we use is Q equal to volume over time. The volume that we get is 680 micrometer cube. We divide by 2.25 second, and the result that we get for the flow rate for water jet is 302.222 micrometer cube per second. Next, we calculate the velocity of the water jet. The formula that we use is velocity equal to flow rate over the area. The flow rate that we get before this is 302.22 micrometer cube per second, and the area that we get in for the pipe is 0.020 meter cube. So after the calculation, we get the velocity for the water jet is 15.111 meter per second. Lastly, the calculation of the water jet is we calculate the pressure. We use the formula is pressure equal to rho multiplied by G multiplied by H. That I mentioned before this, the density water that we use is 1000 kilometer cube. So we multiply 1000 kilometer cube and we use the gravity 9.81, and the height that we get is 0.93. So the pressure for the water jet is 0.123 kilopascal. Next, we go the straight line configuration. Alright, for this project straight line, the diameter that we use is 3 mm. Area that we use is 7.09 micrometer square. Time taken for this project is 2.25 second. Height that we get is 4.25 meter. Volume that we get is 0.185 micrometer cube. Density that we use, rho, is equal to 1000 kilometer cube. Same like before, we measured the flow rate first. Q equal to volume over time. We divide the volume 0.185 micrometer cube divide by 2.25 second, and we get the flow rate for the straight line is 82.222 nanomicrocube per second. Next, we calculate the velocity. Velocity equal to flow rate divided by area. 82.22 nanometer cube per second divided by 7.0969 micrometer cube, and we get the velocity for the straight line is 11.631 meter per second. Lastly, for the straight line calculation, we measure the pressure. Rho multiply by gravity multiply by height, and we get the calculate value for this pressure is 41.693 kilopascal. Okay, we move to the closed loop. For the closed loop, we use a diameter equal to 3 mm. Area that we use is 7.069 micrometer cube. Time taken for this closed loop is 5.32 second. Height that we get for the closed loop is 1.20 meter. Volume that we get is 0.180 micrometer cube. Density that we use is same like the others, is 1000 kilometer cube. Okay, for the flow rate closed loop, we divide the volume, we divide by time is 0.180 micrometer cube divide by 5.32 second. We get the flow rate for this closed loop is 33.835 nanometer cube per second. Next, velocity that we get from the closed loop is, we use velocity equal to flow rate over area, 33.835 nanometer cube per second. We divide by 7.069 micrometer square, and the velocity that we get is 15.11 meter per second. Lastly, pressure that we get from the closed loop is 11.772 kilopascal. How we get it? We multiply the rho, g and h, 1000 kilometer cube multiplied by gravity 9.81 multiplied by height that we get for this project is 1.20 meter, and we get the pressure of the closed loop is 11.772 kilopascal. Okay, that's all for this explanation. Thank you.
Okay, Assalamualaikum. So for today, I will be doing for the simulation. Okay, Assalamualaikum. Okay, so for today, I'll doing the presentations. Okay, Assalamualaikum. So for today, I will be presenting about the simulation part. Okay, this is the water jet configuration. The right one is the elbow pipe that I've designed, and the left one is the graph for the elbow pipe. Okay, so this is the pressure that I got from the elbow pipe, the pressure, density and velocity magnitude. Okay, so okay, this is the animation for the elbow pipe. This is the inlet and this is the outlet. Okay. Okay, next, closed loop configuration. Okay, the right one is the T-pipe design, and the left one is the graph for the T-pipe. Okay, this is the calculation that I get for pressure, density and velocity magnitude for the T-pipe. Okay. And this is the animation for the T-pipe. The two of this is the outlet and the one is inlet. Okay. So that's all from me. Thank you.
Hi, Assalamualaikum. My name is Nur Syairah binti Abdul Jalil and my metric number is B0820103883. So for today, I will present my part, which is for discussion and conclusion. From this project, some experiments have already been done using the pipe to discover pressure, flow rate and velocity in various types of pipe. Based on Bernoulli's principle states that the total mechanical energy of the moving fluid comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. So for this experiment, we use Bernoulli's equation to get the results and comparison for each type of pipe. Next, we'll use the data we gathered to create a water jet. Meanwhile, while the velocity of the straight line configuration is lower than the closed loop configuration, the flow rate of the straight line is larger than the closed loop. The area of this pipe is the same, but the number of holes is different. We may conclude that the straight line has more pressure than the closed loop since the closed loop has more holes than the straight line. The simulation component reveals that the water jet configuration has a higher pressure and velocity magnitude than the closed loop because when additional holes are added to the pipe, the pressure and velocity of the flow water will gradually decrease. As a result, we were able to effectively complete the experiment, which included setting up the pipe installation for water jet, straight line, and closed-loop configurations. We also know how to compute and quantify flow rate, velocity, and pressure at each pipe. We studied the Bernoulli principle using the Bernoulli equation to determine and compare the pressure variation in a pipe based on the results. We were also able to recreate the experiment for the simulation portion, which helped us better comprehend the concept. As a result, the straight line water hose structure allows for a higher water flow rate, whereas the closed loop allows for water flow to be slowed.